Chris Bachman. I'm a professor in mechanical engineering at Cal State LA, and I'm also the advisor of the Formula and Baja teams there. And I've worked with the technical editors at designjudges.com to put together an article and this presentation on how to design strong, stiff, and light structures and joints. So let's get into it. So the most important consideration in design is to use the right process, and that is the engineering design process in this case. And there are many different formulations of the design process, and your organization likely uses something similar, but not identical to what I'm going to show here. But the most common mistake made by inexperienced designers is to only get a general idea of your objective, and then to begin creating a solid model and performing stress analysis on the first idea you have. When you do this, you're really going to miss out on developing a much better solution, and will often spend a lot more time iterating in the detailed design phase than you gain from skipping the first two phases. So you can see here in the four phases that I roughly break them into. So during the first phase, your team will fully define the problem, and you'll do this through identifying your objectives of your group, performing background research, which can include back-of-the-envelope calculations, getting input from experts and users, et cetera, and will culminate in the generation of measurable requirements. Keyword there being measurable, with and knowing how you are going to measure them, that your design needs to achieve to meet your objectives. So, and these requirements can also be tiered from high level, and you'll definitely start at a high level of the overall system. And this little plug, we're going to come out with a topic on overall vehicle design. I think that's an important place to start early on in the design process, and you're going to feed those down into lower level subsystem requirements. And these requirements can be used not only to be verified in the fourth phase of the design process, but also in selecting your design concepts in the second phase. And then each of these first three phases can have reviews to ensure your team has done a thorough job in that phase. This one being the system requirements review is the typical name for it, although this can vary, as I said before. And the number of reviews and the depth of reviews will depend on your organization and your organization's goals. So during the second phase, you'll generate as many concepts as you can through brainstorming, researching past designs from other organizations, receiving inputs from experts and users, et cetera. And if you can identify the strengths and weaknesses of your design concepts and designs from others, one thing I like to leverage the design of others very frequently, you can then strategize how to maintain the strengths and improve on the weaknesses of the other design concepts to create an improved design. A design concept is typically then selected after you've generated a lot of options through kind of quantified trade studies. And so those are sometimes called decision matrices. During the third phase, you'll create solid models in SolidWorks or the many CAD modeling softwares that are out there. You'll create detailed drawings, perform analysis and simulation, and prototype and test. It's not uncommon to use less refined prototypes in earlier phases. During this phase, you want to really leverage the power of combining theoretical analysis, computational analysis, or we call them simulations, and testing to give you the highest possible confidence in your design, and that it will meet your requirements, and that will help you use the least amount of time and resources to give you that confidence. During the fourth and final phase, you'll produce your design, verify it meets your requirements. You're going to test and track its performance, and then turn to any of the previous phases to improve your design. And your design can always be improved, and iteration is the most common and effective way to kind of steadily improve your design. And ideally, this whole design process, you're steadily simplifying your design. And that's really because your design is not done and you can't take anything else away from it. Not that you'll ever get to that point, but that'll take us into our next item. So keeping it simple. So there's an infinite number of ways to do pretty much any task. And I love Rube Goldberg machines. Here's kind of a classic cartoon done by him showing a self-operating napkin. I won't go into its details, but really, what does it mean to keep it simple? A few common things are kind of the minimized number of parts, the number of fasteners, how many machine surface you have, keeping things symmetric when possible. One thing I love to do is to use or modify parts that can be purchased off the shelf, not trying to rebuild everything yourself. Leverage the tons of other designs that are out there mass produced. And so there'll always be trade-offs in these decisions, right? And so you should use your requirements to really drive the final decision, right? I mean, so there's some cases where you can't just have one fastener, and there's a good reason to have 2 or 3 or more fasteners, right? So this is just another piece of the puzzle that is the design process. But I'll tell you this: so the best part is really a part that is not there, right? It takes 0 times to make, it doesn't cost any money, and it will never break. So if you don't need it, it shouldn't be on your design. Next, let's talk about the best ways to load material in your designs. And I'm just going to use a couple simple examples to illustrate this. And so on the left, I'm always going to draw just a small piece of material with a few forces on it. And I'm going to do a hypothetical cut, and then I'm going to draw a free body diagram of the left half of it. And so you can see for these two kind of ideal cases, the tension, compression, and shear, that you're really going to be able to hold those forces across the entire cross sections. And so that force is really distributed and shared over the entire cross section. And that's a very effective way to hold the force in a material. And when you're doing shear, keep in mind that if you can, even double shear is better than single, because you can double the area that you're holding it against. And there's other benefits to using double shear too. But let's get into really the ones you want to avoid. So torsion, which is just twisting the material along its axes. Because of its nature, the outer edge will get strained more. It's just going to go a further distance away from the material next to it than at the center. And as a result, the outer edge is used much more than the center. And so what this means is that you're not really using all of your material effectively. So if you want to have a light material to hold torsion, you should put as much of it at the edge as possible. And one that you should just really avoid altogether is bending. So I show kind of a small slug here with a force down at the end. And really you can think about bending. So I just do a kind of a sum of the moments equal to 0. And you have kind of the forces that the moments that are due to these stresses, right? And roughly kind of the forces are sigma times A, although, there could be a little factor for A because you're not using the entire cross section evenly. The bottom down here is going to be in compression, the top will be in tension, but just to get us some orders of magnitude. And then the moment arm roughly is the height. And that's going to counteract this moment here, which is going to be the force times the length, which you could get from a free body over. And so what you'll see is roughly that this stress is going to still be force over area, but it's going to get an amplification of the length over height. And there's actually even a factor of 6 when you start to include that, the moment arm doesn't actually act all the way at the top, but just a slight bit above it, and you're not using all of the area. But that factor will depend on if it's a square or round shape. But really what you can think about is the length over height is really like, you're getting a pry bar and you're getting a huge amount of leverage with this force. And the stress is only going to act at a small bit of leverage. And you're also not using the center. So this should be avoided at all when possible. And if you need to hold it, and there's good cross sections to it, right? You want to take the material out of the center. Like a circular cross section is not a good cross section to hold it bending. You want to take the material out of the middle and put it on the edge. And so that, of course, looks like an I-beam or even a square cross section channel is better for holding that. So there's, engineers have found a way to kind of quickly and easily avoid bending, and that's to use tetrahedra and triangles. I mean, if you just walk around the world, you're going to see, any bridge or structure or crane or shear walls in your house. They're always going to have these structures to avoid bending. And so tetrahedra are great structures because if you apply a force in any direction at the nodes, you're going to be able to react that force with tension and compression. That is not true if you apply a force right into the middle of the tube. Obviously, that tube will bend. Triangles are next best, as forces that are in the plane of the triangle will result in tension and compression in those tubes. But it will react in bending if you push in the direction kind of perpendicular to plane. So, example of an A arm doesn't usually hold too much force that's perpendicular to it, and so it's pretty strong tension and compression. But if you had a suspension node that's pushing in and out on a triangular feature, that might not be as strong as a tetrahedral. And the last one, of course, is bending, right? if you had just a straight tube, these two will be bending this tube, and only pulling it straight out or pushing down will be tension and compression. So using these structures is an easy way to avoid putting things in bending. And in the above example, I showed tubes, but this principle can also be applied to small parts. You'll even find that when you perform topology optimization, you often find parts that result in tetrahedral and triangular geometries. And that should be no surprise. So the next thing I want to talk about is thinking about your load paths. So strong and stiff designs with little mass require careful considerations of the loads that you're holding. So the suspension I show here, which doesn't do a good job of considering load paths, has three forces that are acting at the center of pressure on the tire: vertical, longitudinal, and lateral force. So because that center of pressure might not be in line with the axis of at which the upright pivots, you call that like kingpin axis or steering axis, it's going to be offset. And it's going to be offset for two reasons. One, because the center of pressure of your tire might not be in the center of your tire. So you might have, some pneumatic type scrub and trail, but you also will have mechanical, you'll have a scrub radius and you'll have mechanical trail, which puts these forces away from this axis, which will cause moments. So the first moment I want to talk about is this, this moment that could be on your tire. Which, in the case where you have some scrub radius and you're braking hard, this would be a big force to consider, or sorry, a big moment to consider. And what is this going to be held by? Well, it's going to be held by your tie rod right here. And this tie rod, because you placed the connecting point of the tie rod so close to the axis by which it pivots, you have this tiny moment arm, right? And you've put this at an angle, this tube at an angle to that moment arm. And so because only the perpendicular component of the force in this two-force member, which has forces along its length, is going to be able to hold the moment, you're going to drastically amplify the forces in that member. To add on to make it even worse, this is a long, slender member, so it's also in buckling. And so that's going to make it less stiff, and it's going to make it more likely to fail. So another issue with these load paths is you have this large longitudinal force, which gets reacted at the frame by these two forces like this. And you see that when you draw kind of between the load path here and here, that because you're turning at a right angle right here, you're going to have a bending throughout this structure, really. And even worse is that you're going to have bending on this threaded rod end, right? And so threads really do not like to hold bending. They have a small minor diameter. They have some stress concentrations there, and so this cyclic loading can really easily break this off. And I've had that happened to many of my teams before. Third issue even on this design is this vertical bump force, which is going to get reacted through the shock here, is also going to put this lower portion of this A-arm in bending, as well as the threaded portion of this rod end. A rod end just being kind of a spherical joint with housed in a piece of material that has a thread at the end of it. So, all right, so that's what not to do. Well, how do we improve this, right? So, simple things is, first move this location that holds the moment away from the axis of which it rotates. So move your tie rod, further away. Right, it gives you a bigger moment arm. That's going to decrease the force. The other thing is move this tie rod perpendicular to the moment arm. That's going to reduce the force in it needed. The other thing you can do is you can switch out these threaded rod ends for spherical joints or called swivel joints and house them in the tubing. And so this is of course still in bending, but you don't have thread no longer in bending. If you really wanted to go to the max on this, you could really even mount a push rod or pull rod type system that mounts directly on the upright, in addition to not using these kind of over constrained A arms and having members connect right to their own nodes, 4 of them. And then you'd actually have, restrict the 5 degrees of freedom and control the 6 degree of freedom with the shock, all through things acting purely in tension and compression. And if you want to go even further, you don't necessarily need the axis by which it rotates to be in the center always. You could push that way off to the left here, and you can even move the connection point to hold the moment about that axis to the front, and that will give you the largest possible moment arm. But of course, you also have a lot of suspension and steering kinematics to consider, and so of course this is part of the design process is that there's trade-offs. Next, I want to talk about how to select factors of safety. So one things that you need to consider is how certain are you in your estimate of the factor of safety for your design. Things that go into this are, how well do you know the loads? How accurate is your analysis method? Have you verified things with testing, etc. The other thing to consider is how much risk of failure are you willing to take on? Are people's lives at risk? Is there a lot of money on the line? Is there PR on the line for your team? And so when you have a lot to risk, then of course you want to play it a little more on the safe side. The last thing is, how sensitive are you to the mass of your design? Because anytime you're going to higher factors of safety, it's going to require you to go to higher masses. And really, to have the highest certainty in your estimate of the factor of safety, you need to understand all the loading cases, and you need to combine that with computational results, testing, and theoretical analysis. And even fatigue analysis should be done for parts with cyclic loading, and especially non-ferrous materials which don't have endurance limits. And ferrous materials typically have endurance limits near half of their ultimate strength, although these general rules should always be double checked, but that's a pretty common one that is seen. And so I want to show one example where, let's say you have this factor of safety of 1, and then you might be very risk adverse, so you do not want to go below it, and you're not very sensitive to mass, so you're willing to go way above it because you don't care how heavy it is, but you also really don't want to go here. So here might be like your target factor of safety when you have a high certainty. And so these curves are supposed to be normal distributions with the probability of the true factor of safety, because you're never, in the end, all models are wrong, but some are at least useful, right? And so you have this model for what you believe the factor of safety is. And if you have some tight error bars on it, then you can actually push closer and push down to the left closer to 1, and you're not going to take on a risk that there's any chance of failure, because the area under this curve is the likeliness of failure. Let's say you have this very large range in uncertainty, which would be the case, I think, for a lot of teams. You're not testing a lot of things. You're not, you haven't been doing stress analysis for a large portion of your life, right? And so because there's this larger uncertainty in what the true factor of safety is for your parts, you're going to need to push your target factor of safety up to be a little bit higher. Now, if you're willing to take on a little more risk, you can begin to push the tail of some of this distribution below 1. If you're willing to have, your parts fail, then, the percentage of this, this is 10% of the curve's area. You push this down here, you're going to have a 10% chance that it might fail. And you might do this when, you can take on risk, or when your goals are very sensitive to mass. But one thing you should keep in mind is you should, just not move on to the next step in the design process when you find the minimum factor of safety of your design is above your target, or especially if it's below it, right? You don't want that. So you should always, if it's above it, attempt to lower your factor of safety to your target, and to have that factor of safety throughout your part if you want your design to be as light as possible. And you can perform to all the optimization, but you can also find where there's little stress in your part and remove the material in those locations, and then add material to hold the loads where you believe you can hold them in tension and compression and shear through looking at the load paths, and then reanalyze your design and iterate. Kind of just as a quick reference, just to give you kind of the range of numbers, unmanned space applications where they're highly sensitive to the mass of their design, and they can complete extensive testing and analysis. They might go down to factors of safety of around 1.1 for yielding and 1.5 for failure. So that's based on the ultimate strength. But that's probably not the case for most of the teams here. They do not have that certainty in the true factors of safety of their design, and and they're not as sensitive. You're not going to be as sensitive to mass as they are, and you have a person's life on the line. So ground applications, systems, and vehicles can have factor of safety usually in the range of 2 to 5, and you can even have safety equipment that has factors of safety up to 15. So there's a range, and you need to use your engineering judgment and your organization standards to help you make the right choice. So Next, let's talk a little bit about the loading of fasteners. So the design of bolted joints can include so much. I mean, you could spend your whole year just designing one joint. But because it includes stress analysis of the fastener and the joint material, the joint stiffness, the joint friction, the bolt grip length, bolt torque specifications, where the proof strength is important, and whether to use positive locking features and use locking nuts or safety wire, et cetera. And there's a great document on all of this in the FSAE series resources from Michael Black called Threaded Fasteners for FSAE, which I highly recommend reading. It's much more detailed than I'm going to go in here, but I'm just going to mention a few best practices and common mistakes to avoid to help you in creating strong joints. And so the first thing I would consider is, the first thing I'm going to mention is, do not use bolt heads to hold the moment. So forces perpendicular to the axis of the bolt should go through the center or be in line with the bolt pattern when possible. So let's start on the right of some bad ones. And so keep in mind in this lower one, I'm just showing the force that's horizontal. I'm just showing the one component just for simplicity. But let's say you have this clevis, and you have some force acting at the center of it in this direction. And so in the top view, it's going along here. And so you think, oh, I'll just put one big bolt, I can make it strong enough. Well, the issue here is that in the side plane, the horizontal component, obviously it's acting up in this plane too, but just for simplicity, you're going to be reacting this force over this length with bending in the head. And so you're really going to be prying this head off and breaking this head prematurely. And the same thing would happen if you use two bolts, but you put them not in line. So here I'm going to look down this direction. And so there's still a component that's off, that's perpendicular to the axes, that's going to be reacted by the bolt heads. So what you can do is you can put all of your bolts in line with this force. And then when you look from the side, your bolts will react with tension compression. The issue here is this force may not just sit in one direction at all times. It might move around slightly. And so what you want to do in that case is use a bolt pattern and have this go through your bolt pattern. And that way, you don't have to worry about it moving out of line, and you hold things in tension and compression. But here, there's obviously a trade-off. Here you have the least number of fasteners. Here you have the most, more complexity, more cost. So yeah, use your engineering judgment there. One that requires less engineering judgment is to not shear the thread. So when you specify, being careful with the length and type of bolt that you're using is very important. And here's one easy example where you might just go grab a fully threaded fastener, and you might try and use it to hold some shear forces. And so you do not want to do that, because the thread has a minor diameter, which is much less than the major diameter, and there'll be stress concentrations from the changes in shape there. And so make sure that you're using the shank to hold the shear of a bolt. And if you're not using the friction, you're not clamping this together and using the friction, you might just consider using a pin instead. You don't necessarily need the threads in that case. So another kind of common just length of the bolt mistake is that you want to make sure you have at least 3 heads extending out of the back of your nut, as these first couple of threads are not going to be full threads. And so they do not have the full major diameter. And if they're inside the nut, like here, maybe you have 3 threads that don't have the full major diameter, you're going to drastically weaken it. The one case obviously is if you put this bolt through there and then cut it off flush, then you're going to be okay. But you should not see uncut bolts flush or any bolts really inside the nut. Next thing I want to mention is why to use washers. So one, they'll reduce the wear of your base materials, because obviously the head and the nut are going to spin on these materials and wear them down. But they will also reduce the stress concentrations, especially for tight clearance holes. So here I show an example of a bolt head without a nut and a tight clearance, and you can see under the head of this nut, there's actually a radius. And so if you try and just tighten it down, you're actually going to have this corner pushing in here and interfering with the radius of your head, potentially popping it off. So, and washers will have some space and some radius to them on one side to handle that. Another kind of common mistake that I see is, not designing enough thread engagement. So, general rule, for a bolt in the same material as itself, 1 times the major diameter of the thread at least is pretty good. I mean, for hollow bolt and soft material, you want to, maybe like, a lot of times we're putting steel bolts in aluminum. You might want, at least 2 times, if not 3 times the major diameter. And, even in a lot of critical applications, they'll actually use these threaded inserts. This one's like a key insert where you have these pins that you drive down in to lock it in place. And that'll make your joint a lot stronger. And of course, these are just a general rule, analyzing, the true strength of the material and the stresses in it for any critical application is really, really advised. But I hope this kind of just illustrates the point of, don't have one thread engaged here. And so it's something to think about. Next thing I want to talk about is avoiding stress concentrations. Made this mistake plenty of times, where you design something and it has a sharp corner. And what you'll find is that you'll have the stresses will be higher at any discontinuity in shape or quick changes in shape. And so you'll have higher stresses, and it's a place for, it's a good place for fatigue loading to have a crack propagate. Right. So here's some examples of, make sure just to add radiuses where you can. Another common mistake is to not think about how close your hole should be to the edge of your material, because it can actually tear out the side. If I'm just kind of quickly doing a design that's not critical, I'm typically using about greater than 1.5 times the diameter from the edge, and greater than 3 times the thickness. But if I'm designing something that is going to see some loads and might be made for other people, and it's going to be holding some shear forces, I'm going to analyze the factor of safety for a tear out. And so it's really just kind of analyzing the shear that's going along that would have to happen to kind of pull this circle outside of the material. All right, next I want to talk about, how to use exact constraint and avoid over constraint. So when you're having kind of some bolted joints, whenever you have over constraint, you're going to result in assembly stresses. And so one common thing that I'm sure a lot of us have experienced is when you have a bolt pattern with a bunch of tight clearance holes, you'll have your first one will line up, but when you go to your second one, it won't line up, and you're going to try and put the bolt in sideways and then crank it down or force the material. And so you're going to have stresses in the part already as a result. Or another common we see is multiple countersinks. And so this first countersink will actually completely line up the hole right here. When you go to put in the second countersunk bolt, it's going to be slightly off center, and it's actually going to press just on one side of it. So typically what we do instead is use one tight clearance hole, and then you use or like a registering feature that kind of specifies the position at one point. And then you can use a slot or some looser clearance holes where you can. And so the slot is nice because for these plates, they'll rotate and they'll find the spot. And so you can get the exact positioning accurately, and you do not have to ever stress your design just to assemble it. Another example of over constraining your design is if you have 2 plates bolted together that can't rotate relative to each other, you want to make sure that the top hole has a clearance hole or a through hole. What you don't want is to tap both the top and bottom plate, because what you'll find is that when you turn the bolt, the 2 plates will go up and down together, and they'll never actually come and fully go down together. I actually see this a lot when I'm in like woodworking. You'll drill a kind of a pre-drill, and then you'll put a bolt through the wood, and because the screws got threads and both all the way down its shank, then it's actually not going to pull them all the way together. So, actually you should actually drill out the first piece of the wood to be a little bit bigger so you can pull that down tight and get the exact constraint. Another common examples are, if you wanted to make some instrumentation that, could hold a tight position for long periods of times, or you wanted to make some mover that had to go over, uneven surfaces, then I would use 3 legs. So 3 legs, for example, on the surface will always come and sit, and it won't rock. Whereas if you have 4 legs, it's going to be over constrained. It can sit flush on these 3, and then to get the 4th leg not to rock, you'd need some shims. Other kind of common examples are using several bearings when you only need a few. And so because these two will define the position of the shaft, this third one would have to line up perfectly. And so any misalignment will cause the shaft to bend back and forth as it rotates. But of course, there are reasons sometimes where you might have to add more than one. Next, I want to talk about just some ways to make your life a little bit easier. And the first is to use rotational over linear motion. I find that's always easier to design to use linear motion, especially if you want something to work well for long periods of time. And here I show an example of a chain tensioner that pivots at the bottom. And you can imagine it'd be much easier to make some sort of chain tensioner with a turnbuckle of sorts, that rotates, rather than trying to make some system that had to linear slide back and forth. And people probably experience this with dresser drawers and stuff, just how easy it is for them to get stuck. It's harder to make this low friction surface and repeatable motion for linear systems. And so whenever I can, I'd use rotational motion over linear motion. Another thing that I would typically advise avoiding are interference fits. They require careful design, tight tolerances. That they're really hard to disassemble, and you'll need to consider like the tolerancing of a lot of consideration to the tolerancing of the parts, and the resulting range in the potential stresses and joint strengths from the range of tolerances, right? So there's definitely applications where interference fits are good, but it's requires a lot of design to do them right. So a couple of just kind of last things to not forget to do is, always design in tolerance based on the function. In the end, you want your design to achieve your requirements. And so, I even show this really simple part where there's actually 3 different ways to dimension this, and there's not necessarily a right answer here. And really the right answer would be, design based on the one that's is going to get it made to function correctly. Because, if you just use default tolerances on these 3, this would actually result in different sizes of the part being acceptable for your design. So, the other thing is design with manufacturer and assembly in mind. You want to think about how you'll make each feature of your design while you're designing it, and that shouldn't be an afterthought. And you would think about how you'll put it together and take apart your design. And as most people listening to this probably know, vehicles often require a lot of disassembly and reassembly, and you really think yourself later if you only need a small number of tools. And you can do this through like standardizing your fasteners and have designs that are easy to service by providing access to the fasteners and having methods to remove components without having to remove 5 other components. You also want to make sure, I just want to remind you that you're never going to get it right off the go, and so you're going to have to test and iterate, and so don't get frustrated. Things don't go right the first time. That's always the case, and so test, iterate, continually improve. And just kind of my last word of advice is, I think most people here, if they're in FSAE, are pretty hands-on. I'd say continue to do it. The best designers and the ones that I've learned the most from and continue to learn the most from have always been very hands-on. And they, and you will too, learn really to be a better designer by being involved in all parts of the design, build, and test process. So I'm sure I've left out many things here, but I thought I hope this would be a helpful set of things to think about when you're doing your designs. So thanks, and good luck out there. If you enjoyed this video and kind of the way things are described, you can check out some similar videos on our Cal State LA YouTube channel for our Baja FSAE team. We've actually had a team there for 40 years. Our FSAE team is a little bit newer, so we house our videos there, but the videos are meant for Baja and formula teams. And even easier to talk about design for formula, just with all the forces being a little bit more known. But with that, I hope to see everyone at a competition soon. Feel free to reach out if you have any questions or if you have any suggestions.